Hi, today's lesson is on circles. We're all familiar with circles and the three things that define a circle. So a circle is the most symmetric of curves, and what are its main properties? Its distance from its center is always constant. So you take any point on the circle, take point A or B or C or D, all of them are equidistant from a special point called the center. So this is the center of the circle, and every point on the circle is equidistant from it. This distance is called the radius. So all these distances are equal, and that distance is called the radius. What's the diameter? So diameter is a special line that goes from one end of the circle to the other, passing through the center. This is the diameter. As you can see, this half AO is a radius and this half OB is a radius. So the diameter is twice the radius. Area and perimeter of a circle. So these are formulae that were derived many centuries ago. Area of a circle is given by pi r squared. Pi times the radius square. So if I know the radius of a circle, I can find its area. The perimeter of a circle, which is also called its circumference, is given by 2 pi r. It's twice pi into the radius. Since we know that 2r is the diameter, this is also equal to pi times d. Pi times the diameter. The area of a circle is 49 pi meters square. Find the circumference. So I know the formula for the area of a circle. Area is equal to pi r square. And that's given to be 49 pi. So if I divide out the pi's, I get r square is equal to 49, which means r is equal to 7 meters. Once I have the radius, I have total control about all the parameters of a circle. So the circumference I know is 2 pi r. So that's 2 into pi into 7. That's 14 pi meters. The answer is C. A circular hoop is widened evenly so that it now covers 69% more area. So I have a hoop. This is the center. Let's say this is the radius. And I widen it evenly. That means now it's become a larger hoop. This is the new radius. And what's given? That the new area is 69% greater than the old area. So let's say the old area, area 1, was 100. And the new area, area 2, is 69% more. So it's 169. By what percent has the radius increased? So I have to get in the radius into all my calculations. So I know that original area was pi little r squared, because little r was the radius of the smaller hoop. I know that the new area is pi big R squared because I've called the new radius big R. And I know that their respective values are 100 and 169. So let's divide. So 169 divided by 100 is the same as pi big R squared divided by pi little r squared. Cancel the pi's, which is why I divided. So I get 169 small r squared is 100 big R squared. I can take square roots on both sides. I know that the square root of 169 is 13. So I get 13r is equal to 10 big R. So by what percent has the radius increased? So I can say R by R is 13 by 10. If I multiply both sides by 10, I get that's equal to 130 by 100. So big R is 130, if small r is 100. So the increase in big R is 30 for every 100 of small r. So it's increased by 30%. Well, unfortunately, none of the answers are correct. The correct answer is 30%. Sorry about that. Chords, arcs, and sectors. So here's a circle. A chord is a straight line joining any 2 points on the circle. So this is a chord. AB is a chord. This portion of the circumference that is subtended by the chord is called an arc. So if the straight line is a chord, this is chord AB, then this curve is arc AB. So an arc has the usual colloquial meaning in English. It's a part of a circle. What's a sector? If I join the ends of the chord to the center, then this piece of pie that I can cut out, this entire thing, is the sector. So an arc AB subtends a sector at the center. Arc lengths and areas of sectors. Draw my circle, I draw my chord, I draw my arc, and I draw my sector. So let's see, how do I find the length of arc AB? Arc AB. What do you think I need? Well, if I knew this angle, let's call it theta. If I knew the angle that the arc subtended at the center, then it should be easy. Because I know that this arc is some portion of the circumference. So it's some ratio of the circumference, and that ratio is obviously given by the angle it subtends. Because the entire angle is 360. So the circumference subtends 360 degrees at the center. My arc AB subtends theta degrees at the center. So the length of my arc is that ratio of the circumference. It's theta by 360 of the circumference. I know the formula for circumference. It's 2 pi r. So that's my arc length. It's theta by 360 into 2 pi r, where theta is the angle subtended by the arc at the center. Similarly for area. What's the area of the entire circle? Area of circle is equal to 2 pi r, is equal to pi r squared. And since my sector also subtends an angle of theta, so it is a fraction of the entire area. What fraction? Theta by 360 again. So area of sector will be theta by 360 into pi r squared, because it is that fraction of the entire area. So both arc lengths and areas of sectors deal with the fractional angle compared to 360. Once you know that angle, you can find both arc lengths and sectors. Of course, you need the radius, because the radius comes into the calculation in all calculations with the circle. The area of a sector of a circle with diameter 16 meters is 16 pi meters square. Find the length of the arc. So theta, this is my sector, and they want this arc. So I know that the area of the sector is theta by 360 into pi r squared. They've given me the diameter. Diameter is 16. So the radius is 8. So the area which is given as 16 pi is theta by 360 into pi 8 square. That's the information given. Let's divide out the pi's. I'll take the 8 square onto the other side. So I'll get 16 by 8 square is theta by 360. I won't calculate theta because I know I need theta by 360 in all further calculations because that's the ratio I need. So I'll keep it as theta by 360. They want the length of the arc. So length of the arc is again theta by 360 into length of the circumference, which is 2 pi r. So I'm going to be lazy. I'm going to use theta by 360 as given here. So I get 16 by 8 square into 2 into pi into 8, which is the radius. So 1/8 can be divided out. The 8 and the 16 can be divided out. So I get 2 into 2 pi, which is 4 pi. So that's my length of the arc. So I used the formula for area to find the ratio theta by 360. That same ratio went through for the arc length. And I found my arc length. The radius was given. Similar question. The area of a sector of a circle with diameter 16 meters is 16 pi meters square. Find the perimeter of the sector. Okay. So here's our sector, here's theta. This time they don't just want the arc length, they want the perimeter of the sector. So what's the difference? The perimeter of the sector is the arc length plus 2 radii. It's AB plus AO plus BO. So it's arc length plus radius. Since the values are the same, we found the arc length in the previous question. That was 4 pi. I'll just add the radii to it. So it's 16 plus 4 pi meters. Of course, if this question was standalone, I would need to do all the working as I did earlier to find the arc length and then just add the 2 radii. An arc subtends an angle of 75 degrees at the center of a circle. So now they've given me the angle. That's 75 degrees. And the circle has circumference 24 pi. Find the area. So I use the circumference 24 pi, which is equal to 2 pi r. I need the radius, remember, to do any calculation. So I'm going to pull out the radius from here. So the radius will turn out to be 12 inches. Now that I know the radius and I know the angle subtended at the center, the area is simple. So area of sector is equal to theta by 360 into pi r squared, which is 75 by 360 into pi into 12 into 12 r squared. 12, 36 gives me 3, 3, 12 gives me 4. So I have 75 into 4 pi. That's 300 pi divided by the 10. There's a 10 left here. That's 30 pi. So the area of the sector is 30 pi inches square. Let's not forget the units. So this question was relatively easy. I used the circumference to pull out the radius. I used the angle theta to find whatever I needed to about the sector. Find the area of the blue region if the radius of the circle is 8 and angle AOB is 60. So they've given theta is 60 and they've given the radius is 8. They want the area of the blue region. What's the area of the blue region? Well, it's the area of the sector minus area of triangle OAB. If I subtract the area of triangle OAB from the entire sector, then I'll get the area of the blue region. Okay, so let's examine the triangle closer. So it's a triangle. Both these are the radii, 8 and 8. So it's an isosceles triangle. Its angle is 60 degrees. So since its base angles are equal, they are also equal to 60 degrees. So we have an equilateral triangle. Angle OAB is equilateral. I know the area of an equilateral triangle if I know its side. If its side is 8, I can find its area. So its area is root 3 by 4, 8 square. That's the area of an equilateral triangle. Root 3 by 4, side square. What's the area of the sector? Well, the area of the sector is theta by 360. That's 60 by 360 into pi r squared. So pi 8 square. Let's see how lazy we can be. I'll pull out 8 square common. 60 by 360 is 1/6. So it's pi by 6 minus root 3 by 4. I'll have to do some working and find out the answer. Tangents. What are tangents? A tangent is a line that touches the circle at exactly one point. So it's very different from a chord which touches the line in 2 points. So here are 2 tangents. Here's another tangent. What's special about the tangent? Well, the tangents are lines not only which touch the circle in one point, but if I join that point to the center, I get a right angle. So the tangent and the radius meet at right angles at the point of coincidence, the point of intersection. So here's an external point, let's call it A. Here's the center O. So AX, AY are 2 tangents drawn from A. So AX is perpendicular to XO. AY is perpendicular to YO. Suppose call this point B and this point Z. Then BZ is perpendicular to ZO. Every tangent and the radius from that point where it touches the circle are perpendicular. That's one property. The other important property of a tangent is, if I connect 2 tangents from a common point, like from here A, I've made 2 tangents to the circle, one is tangent AY and the other is tangent AX, then these 2 lengths are equal. So AY equal to AX. Since AY and AX are tangents from A to circle O. So the 2 tangents that can be drawn from an external point to a circle will have equal lengths. Find the length of OB if the radius of the circle is 30 inches. Firstly, everything is given in feet, so I'll convert 30 inches to feet. 30 divided by 12, that's 2.5 feet. So the radius is 2.5 feet. Now I'm not going to mess up on units. AB is a tangent. That's clearly seen, though it should have been given in the statement, but AB is a tangent. So what do I know? I know that the tangent is perpendicular to the radius. So I know that this angle is 90 degrees. AB perpendicular to AO. So now it's easy. I have 2 sides of a right angle triangle. I need to find the hypotenuse. OB is the hypotenuse. So I know that OB square is 7 square plus 2.5 square. That's 49 plus 6.25. That's 55.25. Now I go to my answers. Look at B, it's 8.10 and all these are increasing. So can the answer be B? No, because the root of 64 is 8. So OB, being the root of 55, will be less than 8. The only answer less than 8 is 8. So the answer is 8. 7.43 feet. Of course, you have a calculator, you can quickly calculate it. But here we see we don't need to because the answer choices helped us. The points E and F are the midpoints of chords A, B and C, D respectively. EF passes through the center of circle O. Find the length of the radius of the circle. So I need the radius, so let me draw the radius. I'll draw one radius and I'll draw another radius. I've drawn two radii, both equal in length. Let's call it R and R. Well, I know a property which can easily be proved, that the radius bisects the chord at right angles. Can easily be proved by showing that two triangles are similar and so on. So I have two right angle triangles. And I know this length is given as 17. Let me call this part x. So this part is 17 minus x. So I've taken EO to be x. So OF is 17 minus x. Because I know EF is given to be 17. Now I have two right angle triangles. I'll just use Pythagoras theorem twice. So in triangle AOE, I get 5 square plus x square is equal to r square. In triangle COF, I get 12 square plus 17 minus x square is equal to the radius square. The radius is the hypotenuse in both cases. So since the left hand sides are both equal to radius square, I can equal them. So I get 5 square plus x square is equal to 12 square plus 17 minus x square. I can of course solve this for x. The x squares will cancel. I'll get a linear equation in x and I'll solve it. That's easy. But here's a quick way. Look at the 12 and the 5. And I know that these two numbers add up to 17. If I took x as 12, 17 minus x would turn out to be 5. And I'd be done. I'd get 5 square plus 12 square and 12 square plus 5 square. So just by looking at it carefully, I got x equal to 12. Now x is 12. What's the radius? I plug in 12. So the radius is 5 square plus 12 square is equal to radius square. So that's 25 plus 144. That's 169. So the radius must be 13, square root of 169. And actually that's what gave me the clue. When I saw 5 and 12, I know my right angle triangle. 5 square plus 12 square equal to 13 square. So that triggered off that I needed a 12 here and a 5 here. Of course, the other way to do it is to just solve for x. You'll solve for x, you'll get x equal to 12. Remember, they're not asking for x, they're asking for the radius. So you better calculate the radius and give it to them. Okay. These are very commonly asked questions where they relate two different shapes. In this case, they're relating circles and squares. So they often involve a circle within other shapes. What's given here? The outer square circumscribes the circle and the inner square inscribes the circle. What does it mean? That means the outer square just touches the circle. It does not cut it. And the inner square also just touches the circle. It does not cut it. If the area of the outer square is 200, what is the area of the inner square? So they've given us information about the outer square and we need to find information about the inner square. And what's connecting the outer square and the inner square? A circle. A circle lies in between, which is touching both squares. So we got to move from the outer square to the circle and then from the circle to the inner square. Let's first use the information given. Area of outer square is 200. An area of a square is side square. So the side is root 200. That's 10 root 2. I'll keep it as 10 root 2. I will not play with decimals. So the side of the square is 10 root 2. Relate the outer square to the circle because I got to move towards the inner square. So the side of the square is what of the circle? Well, this is also the side of the square and that's the diameter of the circle. So diameter is 10 root 2. What do I need? I need the area of the inner square. So basically I need the side of the inner square. Well, look at the sides of the inner square. This is the side of an inner square. This is the side of the inner square. How is it related to the circle? Let's draw a diagonal of the square. And the diagonal of the inner square is the diameter of the circle. So this D, which is the diameter of the circle, is the diagonal of inner square. So this is the big step in the question. The big step is to relate outer square to circle and circle to inner square. And I've done that. The side of the outer square was the diameter of the circle. And the diameter of the circle was the diagonal of the inner square. So now let's find the side of the inner square, or let's just directly find the area of the inner square. Let's call the side of the inner square x. So I know that this is the diagonal. I use Pythagoras. So I know x square plus x square is equal to diagonal square. So 2x square is equal to 10 root 2 square. That's 200, which was the area of the outer square, if you recall. So x square is equal to 100. Do I need to find x? No, I need to find the area of the inner square, which is x square. So my answer is 100. B. A regular hexagon is inscribed in a circle. So here's another example of relating a polygon to a circle. If the area of the hexagon is given, what is the diameter of the circle? So I know the area of the hexagon and I need to figure out something about the circle. And the hexagon is inscribed in the circle. So let's just draw diagonals of the hexagon, which also, because of the symmetry of the figure, I know these 6 triangles are equal. And this is the center of the circle and the center of the hexagon. Since the circle circumscribes the hexagon, this will be the center of both. What do I know about this one triangle? It's an equilateral triangle because this is 60. These two are the radii. So these are also 60 each. So I found out something very important, that the radius of the circle is the side of that equilateral triangle. So radius of circle equal to side of equilateral triangle. All that's left to do is relate the information given. What's the information given? The area of the hexagon is given. Area of hex is 150 root 3. From the area of the hexagon, can I find the area of the equilateral triangle? Of course, because the hexagon is made up of 6 identical equilateral triangles. So area of equitriangle will be 150 root 3 divided by 6. That's 25 root 3 centimeters square. So I know the area of the equilateral triangle. From the area of the equilateral triangle, that's this. Can I find out its side? Of course I can, because the area of an equilateral triangle is √3/4 side square, and that's equal to 25√3. Let's divide out the √3's. I get s square is equal to 100. S is equal to 10 centimeters. So I now know the side of the equilateral triangle. What's the side of the equilateral triangle to do with the circle? The side is the radius. So this is the radius of the circle. Is that what they're asking? No. What are they asking? They're asking for the diameter. So the radius is 10. The diameter is 20. The answer is C. Okay, so we are done with circles. We looked at some important properties of circles like lengths of arcs and areas of sectors. We related chords. We discussed some tangent properties of the circle. And finally, we discussed how circles and other polygons fit with each other.